So, in the previous class we looked at so-called 3-element matches, right? We found that L-match circuits do not have the requisite degrees of freedom to set the quality factor of the match also. So in other words, the bandwidth of the match cannot be set independently. Okay. If you go back and check, the bandwidth of the match is purely set by the ratio of resistors. Okay. So you need a third element, okay, to add another degree of freedom to set the Q independently. And we saw that the Q is the sum of conceptually the sum of two Qs, left side L match Q and a right side L match Q. Okay, and you can show that the overall Q is the sum of the quality factors. Okay, and we kind of did and I guess looked at it very quickly. So maybe in this class, today's class, we'll do an example, right? We'll take the same impedance matching that we did with the L match, and then we'll do either the pi match, any one of them we'll do, okay? And then we'll see if there are other types of matches. So just to refresh, there are two types of pi matches. Low pass or high pass. Okay, similarly two kinds of T matches also. You can think of this as being split with some intermediate impedance Ri, okay, which is used to calculate QL and QR. Okay, so we will use that in an example in today's class. So let us go back to the L match and see. Yes. So we said 50 ohms to 200 ohms at 1 gigahertz. Okay. We did the two L matches. So let us do the same thing. You folks want to do pi match or T match? Let's do pi match. Right? T match is the exact same procedure. Okay. And let us say we'll do the low pass pi match. Low pass pi match, F is 1 gigahertz, RL is 50 ohms, RN is 200 ohms. We will set this quality factor. What quality factor did we have in that case? I think we had √3 if I am not mistaken. So let us do something 1.7. Okay, so we'll get a much more narrow band. Shall we say 3? Right? Or 5? Okay. Let's choose a Q of 5. Okay. We'll see how to tackle this. So, I said low pass L match. So, right, this is your circuit. In the end, you are going to add L1 and L2 and use a single inductor of value L1 plus L2. And you are going to have some intermediate impedance Ri. How do you calculate Ri? It is simply the sum of the two Qs. We know that the intermediate impedance for a pi match is going to be smaller than the individual resistances, load or input resistances. So, Rn by Ri minus 1 plus, because each of those individual L matches are from load to Ri, it is a step down transformation. Okay. From input to Ri, it is also a step down transformation. Each of those L matches are step down L matches. So Ri has to be lower than both. Okay. So in our case, this is the equation we need to solve. 200 by Ri minus 1 plus root of 50 by Ri minus 1. Okay. How do you solve this? How do you solve this? Square and add, square and add. I think you'll have to square twice. Please do it. Please solve this. I want to find out the value of Ri. Please solve it. Huh? About 15 ohms? Is it exactly 15? 15.2. Okay. So, huh? 50? 2.04. 2.04. But if you put in 2.04 here, do you actually get a Q of 5? If you add these two, If you put in 2.04, will you actually get a Q of 5? One of them will not be an actual solution to the original equation. Isn't it? Because 200 by 2.04 is about 100. So root 99 is already much larger than 5. So one of them is not a solution. It actually gives you a negative root. And when you add the two roots, that will be a root. You take the negative square root. Okay, so that is not a valid solution. So 15.2 is right. Okay. What do you do next? Very simple, design the two L matches. Right? So, go back to this guy here. The first L match, the right side L match goes from 50 to 15.2. Do you know how to design that L match? You can find out. Yes? Do you know how to take down 200 to 15.2 from L1 and C1? You know how to do that. Right? You add L1 and L2, you get the overall pi match. Very straightforward. Will you be able to do this as a homework? I hope you will be able to. So now, if you have designed this, design the two L matches. Right? The reason is very simple. At the frequency of interest, the right side L match makes that 50 ohm look like a 15.2 ohm. So now you can design L1 and C1, right, as an L match. Take the other guy, you know how to design from 50 to 15.2 also. Pretty straightforward? Okay. I'll leave this as a homework. If you have any questions, ask me in tomorrow's class. Okay? Any questions about this? Everything hinges on finding out the value of Ri. If you did the same thing as a T match, Ri will be larger than 200. Go up from 50 to maybe 400 and come back down to 200, something like that. Okay? Okay, good. So, pi matches should be pretty straightforward. So, if you design this, you will find that you have designed an impedance transformation network at a particular frequency for a particular Q. Okay? Note that you have a down transformation and then an up transformation. I think I mentioned this in passing last class. If the Q gets higher and higher, the value of Ri will keep getting smaller and smaller. And that is pretty much obvious from this equation. If you look at this equation, right, if your left hand side 5, the value of Ri has to get smaller. You have the sum of two square roots. 250 do not change. Ri has to get smaller if the overall Q gets larger. Okay. What will happen is that as a practical matter, you cannot get a larger Q than a specific value. If Ri gets to be like an ohm, okay, or a couple of ohms, just a wire connecting to an inductor and a capacitor can easily have several hundreds of milliohms if you are not careful. Okay. So you may find that at that point you hit the reliability or limits of what you can reliably design. Okay, which means that there is a limit on the upper quality factor. Number two, what we have not discussed so far, we have assumed that are ideal. If they were not ideal, imagine now that L1 and L2 themselves have some series resistance. How are you going to build an inductor? You are going to wind a wire around a magnetic core. On the integrated circuit, you do not have a magnetic core. What do you have? What do you do if you don't have a magnetic core? How do you build an inductor if you don't have a magnetic core? You wind it around a non-magnetic core. That's all. The magnetic core helps you because it has a mu R. Just like you create a capacitor by putting a dielectric. Right? So epsilon naught, epsilon R by A in times area of the plates over distance between the plates. If you don't put a dielectric, right, the density will be lower, epsilon R is 1, you only have R. Similar to that, if you actually wind a wire around a magnetic core, the relative permeability of the magnetic core will actually improve the inductance for a given number of turns. If you don't do that, if you just do it around R core, you do have R core inductors, you will get a much smaller inductance for a given area, which is what happens on the integrated circuit. You do not have a magnetic material. Okay, so you pretty much just wind it around R. How do you wind it around R? You don't have a 3D. You cannot make a solenoid, right, or any of those 3D shapes. Okay, so what you can do is planar concentric rings can be made. Okay, which is what you do, and we will discuss that separately in a separate class much later on in the course. You don't need it right now. Okay, maybe in a couple of classes I'll come back to it. Okay, so there are fundamental limits on the Q that you can achieve. Okay. Finally, I also mentioned transformer matching. Okay, and indeed transformers can be used to match the match impedances. Okay, very commonly used. But since you folks know it already, I'm not going to specifically teach it here. Of course, there are specific design parameters, okay, which you will learn if you ever need to apply it in practice. Okay, I will not cover it separately here. Yes. You can't. Okay, unfortunately you can't. Okay, as you can see, the overall Q will define Ri. Okay, but imagine that the Q of L2 is such that this has a series resistance. Then the value of Ri that you can get, there is a fundamental minimum value of Ri that you can achieve. Okay, you cannot get lower than that. Okay, so even if RL was transformed to 0, you will get the series resistance of L2 for that series resonant network. That is a fundamental limit, which means there is a limit on the highest Q achievable for this circuit. There is a limit on the lowest Ri achievable for this circuit. Okay. Now, the good thing about these types of matches, okay, on an integrated circuit, these types of matches can be used to match even for discrete circuits. The advantage is on integrated circuits, you do custom design of C1, L and C2. If you are doing discrete design on a PCB, you only have discrete values of L and C that you can choose. Okay, you will choose the nearest value and move on. Okay, if you are doing it for integrated circuits, you will design C1 custom, C2 custom, L custom. Okay. It turns out that there is a fourth type of, or a third type of, okay, so we saw L match, we saw T match, pi match, so this is the fourth kind, right, fourth kind of match called the tapped inductor or tapped capacitor match also. That will also be, okay, so the tapped capacitor match will look like this. Okay, it turns out if you had the option of changing your L1 by L2 or L2 by L1 plus L2, effectively, if you had the option, imagine that you have a large inductor and you have a tap from inside that. Okay, so now what I mean is I have shown it as two separate, but now imagine that it was one single inductor L broken up by moving this tap up and down. Okay, if you had the option of changing that tap, it turns out that the input impedance would keep changing as you change that tap. Okay, and it turns out that in the ideal it would be a function of L2 by L1 somehow, or L2 by L1 plus L2, which is the same thing. Okay, so that is why it is called a tapped inductor match, capacitor match. Okay, but what we will do, we will approach it from what we have seen before on the L match and pi match and so on. How do you deal with, so the way we started looking at matches, you started dealing with circuits that are non-ideal series or parallel resonant networks, right? As in you don't have a pure series or a pure parallel, you had something which was a hybrid. We try to convert either a full series or a full parallel. How would you, let's start with the tapped inductor for example. How will you convert this into a pure series or parallel network? Any ideas? Yeah, so you have to do a whole bunch of transformations now. It's not just one or two transformations. You take these two guys, convert them to a series equivalent. Then you add L1 to that. You have another series. You convert that back to a parallel. Then you have a parallel RLC. That parallel RLC, if that parallel L and parallel C resonate, you will have a pure resistance. Okay? So, let us quickly write down let's just quickly write down the steps. Okay, so this would now be we will do a series to parallel of this. Okay, so C and L1 will remain the same. I'll call this L2S and RLS, something like this. I need to start giving variable names. What do you do next? So you combine L1 plus L2S. Okay, so this is now a series combination. That would now become a fully parallel combination. Okay, this is now a parallel resonant network. So Rn is equal to Rp at resonance. So this resonance is such that C resonates with Lp. Okay, very good. Our problem is to find out the values of C, L1, L2. Can you please think and suggest a way based on what we know? There are 3 degrees of freedom, correct? C, L1 and L2. So we should be able to set the overall Q, overall the frequency and the impedance transformation ratio, correct? So these are the specifications. 1 gigahertz, let us say 1 gigahertz, Q of 5, 200 by 50. Right? How will you start? So what I am asking you to think, based on these 3 parameters and based on the equations that you know, we should be able to find out the easiest way to calculate out these values, correct? Yeah. We know RL and RP, of course, right? Okay. So the easiest things to find, you start with the parallel resonant network, the simplified network. Okay, you know RP, the input resistance is RP, that has to be equal to Rn. Okay, So since you know Rn, Rp we already know. Correct? Do you know the Q of the network? Of course you do. So you can directly find C and LP. Okay? So Rp is equal to Rn. You find out. Okay? Okay? Rp over omega naught LP at resonance is equal to Q. You can find out LP. Rp times omega naught C is equal to Q. You can find out the value of C. Agreed? So now we know all the parameters of the parallel network. We know C, we know LP, we know Rp, we know Q. Correct? What do you do next? Huh? So of course we can find out this guy here. We can find out L1 plus L2S, we can find out, and we can find out RLS. Agreed? Yes. Sorry, we don't know? F. What do you mean we don't know F? I'm not able to hear. Can you speak just a little bit louder? No. Okay. So you need to find out C, L1, L2. Okay. When I say set F, these are the design parameters. Frequency of operation, Q and Rn by RL can be set through C, L1, L2. That's what I meant. So F is known. You know your operating frequency, right? So maybe I'll use a different word since that is confusing. Right? We know frequency of operation, we know Q, we know this. We know omega naught, 2 pi times Fs, omega naught. Was that your question? Whether it's set? Yeah, we know. Okay? Okay? What else? What do you do next? We want to find out L1 independently, right? Okay, and so on. Is the Q of the blue circle portion the same as the Q of the red circle portion? It's not. The resistance value is the same, inductance value is different. Right? So you cannot use directly those Q expressions, right? Unless you find some way around it. What else do you know? There is one parameter so far. RL has not been used so far. So please try to think how you use RL. The thing with this is that once you figure it out, it's very straightforward. Yes. Exactly. You know RLS, you know RL. That is just a series to parallel transformation, parallel to series transformation. You know the Q of that. The minute you know the ratio, you know the Q of that. Correct? So for this blue transformation, this is some Q prime. Do you know Q prime? Of course you know Q prime. You are doing a parallel to series transformation. What is Q prime? So when you do a series to parallel transformation, the parallel resistance is the series resistance into 1 plus Q squared. Right? So the Q prime is equal to root of RL minus 1. Agreed? What do you do next? Now it's very straightforward. The minute you know this, since you know Q prime, right, you can find L2 directly. And of course, you will have to calculate L2S also. Since you know L2S plus L1, you can calculate L1. Make sense? Everybody got this? Like I said, once you find out what parameter you are not, there's no way to go wrong. Very straightforward. Okay? Any questions? Tap capacitor match will be similar, as you might imagine. I hope I don't have to do that. Okay? Now, what I will do, I'll probably try to post some notes on the derivation of the impedance. Now what you can do, you can just brute force this and calculate the input impedance of the tapped inductor structure here. Okay? And you can now show that the impedance varies in certain way, but more importantly, why is it a tapped inductor? Then it turns out that the impedance will somehow depend on L1 by L2. Somehow. In an ideal case, if you apply some, okay, it will end up the input impedance will end up depending on some L1 by L2 factor. I'll probably post that. There's not a lot of value to just deriving it, and it will take probably like half a class. I'm not sure there's enough value. Okay. What you can show is that when L2 by L1 or L1 by L2 is very large or very small, you can make certain, right? In this case, when L2 by L1 plus L2, okay, is very, very small, you can make certain approximations. Okay, that is the way it will turn out. Same thing for the capacitor. Now, for impedance matching at the input of an LNA, at the input of a PA, etc., less commonly used matches. Okay, they also have 3 degrees of freedom, but they are less commonly used matches. Having said that, there are specific circuits where they are used. Okay, there are specific types of oscillators where this tapped inductor structure or tapped capacitor structure is used in exactly this form. Okay, the circuit that uses the tapped capacitor structure is called the Colpitts oscillator. That circuit that uses the tapped inductor structure is called the Hartley's oscillator, named after the people who discovered these types of oscillators. And they inherently assume impedance transformation of some sort. Okay. So, to the oscillator portion of the course, we'll probably relook at this in a brief way. Okay, relook this at this circuit. Take a relook at the circuit in a brief manner. Yes. Why can't you use? Why can't you use active elements for impedance transformation? Well, the active elements have 2 problems. Number 1, they are not reciprocal, they are unilateral. Okay, signal comes out on the other side, but the reverse is not true. In some cases you might want that. Okay. Number two, they add noise. Okay. Whereas these passive elements do not add as much noise as active elements. Passive transformation networks have loss. Okay. But you can show that well, we'll come to that. We'll come to what the noise figure and loss relationship is. Okay. But they happen to be, the advantages of passive networks are that they are lossy, but they are bilateral, completely reciprocal, and more importantly, they are completely linear. The minute you put in an active network, these networks matching will be linear. Okay. There are specific cases where this linearity will matter. For example, let us say you are trying to build a power amplifier. Remember, there are two specific cases where I said you will use matching networks. Those are cases that we know of at the edge of the chip, edge of the transceiver chip. So normally that is at the input of the receiver and output of the transmitter. Okay. The output of the transmitter, high power, high swing node. Okay. You do not want to use active matching elements there. Okay. Because they will not be linear at all. So you will end up using passive elements. At the input of the receiver, you are more interested in noise figure. Okay. You want to be as low noise as possible. Okay. That stage, it is indeed possible to do active matching. Okay. Which can sometimes be better than passive matching. I'll put it that way. And we will indeed look at both types of matching. Both active matching networks as well as passive matching networks. Okay. But when I say active matching networks, I can directly design the circuit to have an impedance of 200 ohms or 10 ohms if I so want. Right. You know how to do that. Okay. So I don't need this matching network at all. And there are indeed circuits that do that. Okay. I will leave it at that, because when we come to the LNA portion, you will see the different ways in which we will not be using these types of matching networks directly there. Any other questions? Okay. Comment or topic on the portions on matching. With this, we're almost done with matching networks. Okay. Just one last thing. Let us say I want to design, let us say an L-match network. It doesn't matter, but I have my matching network. Okay. I want to match a real impedance to a complex load. Can this be done? In fact, once you do this, you can also see that you can match RL plus JXL to RN plus JXL. Right? So you can do that. How do you do this? Any idea? Okay. Yes, so if you choose the appropriate type of network, okay, you can indeed match this very easily. Let's see, let us assume that XL, this L is the load, okay, it's not inductive, okay, because it's a load. This could be inductive or capacitive. Let us say XL was positive, okay. In other words, so what you have here is this. This is my load. Okay. Let us say I'm going to do an L match. Let us start with the simplest possible L match. Let us say, which case do you want to take? Let's take the case when, let us say Rn is larger than RL. Let's take that case. Okay. If you had to match only to RL, what kind of matching networks could you choose? You would have the choice of this or this. These are the two types of matching networks you would use. Okay. If you wanted to do upward matching from RL to RN. Right? We have seen these two before. Now, all you have to do, of course, now you are now trying to match right? So let us say this value was C and L. Okay, I'm trying to match to this. I want to find out the values of C and L that will now match to LL and RL. What I do is I first find out values of C1 and L1 that will match RN to RL. Agree? Now imagine conceptually I'm going to split that L1 into L plus LL. Okay, so all is find out the value of L1, subtract the value of the inductance of the load, and then I find out the actual matching network that I need. This will work if L1 is of course larger than LL, inductance of the load. If you go through this calculation and find out that L1 is smaller, you can't do anything. You can't use this. You'll have to go to a more complicated math. Okay. The other one is much more complicated. If you were to do this, this is actually much harder. Okay, for several reasons. Now you will need to design this matching network actually to RL. Okay. Now what you are deciding on is at some particular frequency the impedance of the to compensate for the impedance of the inductance and even more. Right? This is much more complicated. Okay. You will probably not go in for this. If L1 happened to be smaller than L, you will probably go in for a pi or a T match and try those out and then come back to this if needed. Okay. This is much more complicated than that. So the other type of matches you could try are for a so this is the first one. So first type of match. The second type of match you could go for the T match for I suppose. Okay. And find out if L2 is larger than LL. Right? So basically what you are trying to do, you are trying to match to the real portion. Okay. And then moving the portion from that inductance and moving it into the load. So you have basically made the problem into matching real to real, except you are now, whether you count the inductance with the load or with the matching network is all that matters. It actually conceptually it doesn't matter. Okay? You could try this for example. The T match doesn't work. T match and the original L match have the advantage of having the series inductance. If the inductance is larger, you just subtract it, it's easy. If not, you will have to do a bunch of series to parallel transformations and then try to make it work. Okay? That same RL plus J omega LL can be converted to a parallel combination of resistance and inductance. Okay? Resistance now needs to be absorbed into this guy here. Somehow. Okay? And because it's a parallel inductance, this parallel inductance needs to be smaller than the original inductance for you to be able to use the pi match. Are you able to see this? So what I would do, so L1, C, L2. So let me try to move it on the next page. this is my transform network. Okay. So let me call this some L3. So of course L3 is correct. You know that L3 is to be smaller than L2 or LLP. If it ends up being larger than LLP, this matching network will not work. You cannot, if the load inductance cannot be absorbed into this parallel L2. You understand? Yes. Sorry? Okay. Are you talking about here? Here. Yes. Just here, this one. Okay. If you do this, okay, how many degrees of freedom do you have? You have 1 degree of freedom, which is capacitance. What do you think you'll be able to set? Huh? You'll be able to set only frequency, right? You won't be able to set the Q. Okay. So unfortunately that won't work, because you need to be able to set the Q, okay, which will give you the value of Rn that you want in this case, because it's a one single transformation case. Okay. Any other questions? So as you can see, the type of matching network that you choose will also depend on these types of considerations, whether the load is inductive, whether the load is capacitive. And believe me, when you find out that your PA has a capacitive portion also, when you find out that the input impedance of the LNA has a capacitive portion also due to parasitic capacitances, it may be inductive because you may have inductors in the circuit, you will find that these kinds of techniques do come in highly useful. So you have to know these things. Okay. So with that I'll stop here. Tomorrow's class we'll continue with the, okay, so now we need to move on to, tomorrow, because we need to get to the projects, I'll start with LNAs. Okay. But before we do LNAs, we need to understand some system level specifications, then we'll hit LNAs. Okay. By next week we should hit LNAs. Okay. See you folks tomorrow.